This video is an overview, not a deep dive, of Fusion 360 tools, techniques and workflows you and your students can leverage to optimize their extended project work, to unleash their creativity and maximize their potential. This video assumes you've been a Fusion 360 user for a while and are confident using tools like Sketch, Extrude and even Render. If not, you are of course welcome to watch along, but there may be some foundations you need to shore up on before moving on. You'll find lots of resources in the notes below this video, and I'll signpost them as we go along. While relatively new to business, students have always worked in a hybrid manner, splitting their time between home and school, network PCs and their personal devices. Fusion 360 is the first and only integrated CAD, CAM, CAE and PCB software platform of its kind. It's unique for educators because it connects the entire product development process into a single platform, meaning students don't need to download additional software and all the workflow they need is in one. This video presumes you have experience of Fusion 360 and how to design parts, so let's do a deeper dive into the power of the platform to optimize and verify those parts so when students make them, they make them better. Remember, if you need a refresher, you'll find lots of links, including resources like the Learn Fusion 360 in 90 minutes below. So today we'll cover a 5-step approach to design using the lean manufacturing principle, which grew out of the famous Toyota production system. We can use Fusion 360 tools and workflows to reduce the wastage of time, materials and energy. The aim is for students to get it right first time. So let's dive into this example using this multi-tool design. First up, let's apply physical materials to a part and use the inspection tools to double check the part for dimensional accuracy, mass and balance properties. If those details are correct, we can export DXFs of sketches to print and cut out or even laser cut key 2D features. The aim is to physically prototype it fast. If we are happy with the fit, we can simulate forces to explore how our part will respond under loading, and we can even use advanced tools like generative design and automated modelling as your personal design assistants. These advanced tools, however, require their own detailed workflows, so be sure to check out the links below. At this stage, we should be pretty certain that the part we've designed is correct, so now we need to navigate moving from digital to 3D physical. To do this, we'll walk through, in much more detail, how to use the inbuilt additive manufacturing slicing capability found in the manufacturing tab. While 3D printing, or additive manufacturing, is a rapid prototyping technique, everything is relative. And if you have a class of 20 or more students wanting to fabricate every design, it can cause significant bottlenecks. So here's a workflow to tackle that issue. Before I commit to 3D printing the whole multi-tool, there are 3 key features I want to isolate and test, as their dimensional accuracy and physical performance are vital. They are the polygon to hold the nut, the mini prying bar, and a precision measuring feature. You can see I've highlighted these in orange, and in this case they're all clustered towards the bottom of the part. To isolate them, I used the split body tool found in the modify menu. This creates a new body by dividing it through a plane, a face or a profile. Therefore, I created a new plane using an offset plane found in the construct menu. The result is that I now have 2 bodies. I could of course make multiple splits to create many new features, each of which is something you need to test. But don't worry about ending up with lots of bodies. You can combine them again using the combine tool, which is also found in the modify menu. Now it's time to move to the manufacture tab and create a new setup for your 3D printer. To do this, make sure in the additive section, then go to setup and new setup. In the setup dialog box under machine, press the select button and use the search box and filters to find your machine. In this case, mine is a Prusa Mini. Select it using the select button. Make sure you change the model selection from the component and instead select the body you wish to verify, then press OK. We'll ask you to select a setting. Choose one that's close to what you need, but you can edit it later. Then press select. Now you will see the build plate of your machine, and you'll have the option to move the part. You'll note that as you move it, all the component moves, but that's fine. Your setup is now complete. You can now edit your printer settings by right-clicking on the setting you initially chose and selecting Edit. Here you can alter the infill, shells, speed, supports, adhesion, pretty much anything you could do in Cura, Prusa Slicer, or any other specialist software. But this is all within the same seamless platform. You can then select Generate under the Action menu, and wait until the generation is complete, marked by a green tick. You'll then see the estimated print time. If you right-click, you can simulate the additive toolpath. You'll see it only simulates the body you had selected. Lastly, you can choose Post-Process and select how and where you would like the G-code to be sent to. I normally put mine straight on a USB drive to transfer it to the 3D printer. So, to recap, in this video we looked at both a workflow and specific tools to create a lean process, all inside the unique cloud-based Fusion 360 platform. Students can quickly verify their work by applying physical materials and inspect the design for technical information like mass and surface area. They can export their sketches to quickly make physical 2D prototypes to test ergonomics and use the power of parametric design to make updates. They can then leverage industry-level simulation tools to identify issues with structural integrity and deploy tools like generative design and automated design to help develop their topology. And finally, we investigated how to leverage the integrated CAM capabilities found in the Manufacture tab, and we explored a workflow to simulate the efficient prototyping of whole parts and individual features. This workflow has only scratched the surface of what Fusion 360 is capable of. So when you get your students to take a persona-based challenge and design, verify, optimise and make a multi-tool for a skateboarder, a vector roboticist or even a NASA astronaut. If you want to collaborate or you need more help, you can join our community of innovative educators at the Fusion 360 Educator Forum. In conclusion, Fusion 360 is a game changer for educators like you. It streamlines workflows, facilitates design review and feedback, and integrates seamlessly into your classroom. By incorporating Fusion 360 into your teaching toolkit, you'll empower your students to become skilled collaborators and innovators. Thank you for joining me today. Stay tuned for more educational content from Autodesk, and remember, together we're shaping the future of design.